So in this video lesson, we're going to have a look at the beginning of kinematics. More specifically, we're going to look at position, distance, and displacement. So we're going to start by talking about the word kinematics. And so kinematics is actually the study of motion. So kinematics is the study of any type of motion. And so we're looking at describing what the motion of an object is going to look like. So that could be things like how an object is speeding up, how it's slowing down, how far it travels, what speed it gets to, how long it takes to travel a particular distance. And so kinematics is always looking at motion of an object. Okay, so we're going to start with position. And so the symbol for position is actually a lowercase d, and it's got a little arrow over top of it. We're going to talk about that little arrow in a few minutes. But so this symbol for position is a lowercase d with that little arrow over top. Now, so position is always going to be at a particular spot in reference to a different spot. So for example, we can describe the position of the door in our classroom. Okay, and so we could say that the door in our classroom, if we're talking about its position, is say 25 feet to the east of us, okay? Or maybe if we're standing in a different spot in the classroom, it's 30 feet to the west, okay? And it's always based on a particular origin point. So we could be saying that the door is 25 feet to the east from Miss Easton's laptop, or is 30 feet to the west from the lab bench. And the idea here is that we have to talk about the origin or our reference point. Okay. Now you'll notice that when I gave those positions, okay, there are two things involved. So there is an actual measure of distance, okay, so 25 feet, but then there's also that direction. And so we've got this being our measure of how far away it is, and then our direction as well. So whether it's to the east or to the west or to the north or to the south or southeast or southwest, okay? And so that is actually called a vector. So a vector contains something called magnitude and direction. Okay, so the direction is easy to see. The direction is east or west or southeast or 30 degrees southwest. Okay, magnitude is the actual amount in terms of distance. So we're looking at 25 feet would be our magnitude. East would be our direction in terms of the position. Okay. And so that's what that little arrow on top of our position symbol means. That means that we're dealing with a vector. Okay. So vectors have those little arrows over top of them to denote that they're a vector. Now that's different from something called a scalar. A scalar contains magnitude only. So a scalar measurement just contains magnitude, no direction. So a scalar measurement could be 25 feet, but there's no direction to show us that it's in respect to anything else. Okay. When we're talking about units for position, we're going to be measuring in units of length Okay, so again, we're here talking about position. So we're using units of length. So generally that means the meter. Okay, but any other unit of length is acceptable as well. So the kilometer, foot, yards, inches, centimeters, millimeters. Okay, but meter is the internationally accepted unit of measurement for length, as well as the standard unit for position. Okay, and just a reminder here that the short form for meter is that little m. Okay, so we're going to draw a little diagram. Okay, and with this diagram, we're going to be talking about positions. So we are first going to draw ourselves a little line, and in this diagram, we're going to put a house. So we've got our lovely house here. We're going to put a person. Obviously not to scale diagram. A person is not as tall as a house. And then we're going to put ourselves a little car over here. It's going to be a cart, I think. So we'll pretend it's something like a car. Okay, and here we are going to denote that this is the origin. And our person is going to be 330.0 meters from the origin. The person and our cart are going to be 680 meters from each other. And the house and our person are going to be 530 meters from each other. And we're also going to denote that west is to the left and east is to the right. Okay, so we're just using our compass rose there. Now, again, this is not to scale. Okay, so this is a not to scale diagram. But we've got all of our labels in here. Okay, so the first thing that I want us to pull from this diagram is what's the position of the person from the origin. So we're looking for a position of the person from the origin. Okay, so this one we need to denote how far away the person is from the origin. And remember that position has to involve a direction. Okay, so my person is 330.0 meters to the west of the origin. Okay, the next one we're going to do is I want the position of the house from the origin. So now we're going to do, let's just undo, we don't need that. We're going to do the position of the house. So this is going to be the house from the origin. And again, don't forget, it's going to need a direction associated with it. And so the house is 530 meters from the person, but the person is 330 meters from the origin, meaning that the house is going to be 860.0 meters. And again, it's to the west of the origin. So that's going to be our direction there. Okay. Now if we want the position of the cart from the house, so we're going to take it a little bit farther now. So now the cart we know is 680 meters from the person, and the person is 530 meters from the house. And so we're going to get a total there of 1,210 meters. And we're looking at where the cart is compared to the house. And so the direction is going to be to the east. So the cart is 1,210 meters to the east of the house. Okay. All right. Now, this is just talking about positions of objects. okay? But objects rarely stay stationary for very long. Objects are moving around all the time, okay? And position is not going to tell us anything about how an object is actually moving or which direction an object is moving in. It's not going to tell us anything about that. And so that's where displacement is going to come in. So displacement is going to be our change in position. Okay, and so we are going to use the final position, and we're going to subtract the initial position. Okay, so the symbol for displacement looks similar to the symbol for position, but it's a little different. Hold on, I've just got to redo that one. Okay, so displacement is going to be delta D with our little arrow above the top here. All right, so in this, we're looking at positions, but we're trying to take the difference or the change in our positions, and that's what the little triangle symbol is for. So that little triangle symbol is actually a delta. It's a Greek letter, and delta means change, okay? And that means it's going to be final minus initial. Okay, and so if you use delta of anything, that means it's the change in something. You're going to take the final of that and subtract the initial of whatever that happens to be. So in this case, we're looking at position. So we're going to take our final position minus our initial position to get our displacement. Okay, and so it's going to be the change in our position is going to be our displacement. Now, we measure displacement in the same unit as position, so it's measured in meters. Okay, but we have to remember as well that because it's got this little arrow here, it's a vector, which means it has direction. So when we are talking about displacement, we have to think about what the direction actually is. All right, so to actually calculate displacement, our displacement is going to be our final position minus our initial position. And so we're going to use this formula to actually calculate our displacement. All right. Okay, so we're going to do this with an actual example. Okay, so again, we're going to draw ourselves a little line, and we are going to denote the origin. Okay, and we're going to have a person standing at the origin. So we've got our lovely person here. And this person is going to take multiple different trips. And then we're going to talk about calculating his displacement or her displacement. Doesn't matter whether it's him or her. All right, so trip number 1 is going to take our person all the way over here. So this is going to be trip number 1. And in trip number 1, our person is going to end up 1,360.0 meters away from our origin. And this is on the east side, so this side is going to be the west side. Okay, and so our person's going to end up over here, so that's going to be trip number 1. Trip number 2, let's do red for trip number 2. So trip number 2 is going to take our person all the way over here to the west side. And so that's going to be trip number 2. So now our person's all the way over here on the west side, and they're 920.0 meters away from the origin, but on the west side. So that's trip number 2. And then trip number 3, let's make that one green. Trip number 3, we're gonna go past the origin, but not too far past. And so we're gonna end up around here. So this is gonna be trip number 3. And our person is gonna end up, we are 340.0 meters just to the east of the origin. Okay, so those are our 3 trips. Again, they're not to scale, okay? But keep in mind, we're going on trip number 1, then trip number 2, then trip number 3. Okay, so with this diagram, we are gonna look at the displacement. So we're gonna calculate the displacement for trip 1. Okay, so trip number 1, remember we started at the origin and we ended up at a position that was 1,360 meters to the east of the origin. Okay, so to calculate our displacement, we're going to do our final position minus our initial position. Okay, so our final position was 1,360.0 meters to the east of our origin. And our initial position was 0 meters away from the origin to the east. Okay, now to be fair, I could have said 0 meters to the west. It doesn't matter which direction I put in there because it's 0 meters away from my origin. So it doesn't matter whether I use east or west, but I actually want to use east so that you can see that we're able to subtract these numbers from each other because they are both going in the same direction. Okay, so we're gonna get 1,360 meters to the east. Okay, so in trip number 1, we were displaced 1,360 meters to the east of the origin. Okay, and that's telling us where we traveled or where we ended up based on where we started. Okay, all right, we're going to do the same thing, only now we're going to do trip number 2. So we're going to calculate our displacement for trip 2. Again, same formula. We're using our final position minus our initial position. But initial position, remember for trip number 2, is where we were when we finished trip number 1. So if we go back to our diagram, our initial position for trip number 2 is going to be this 1,360 meters to the east. And our final position in trip number 2 is 920 meters to the west. All right, so our final position is 920 meters to the west. And our initial position was that 1,360 meters to the east. Okay, now here's the problem. If the directions are not the same, then you cannot add or subtract them. Okay, and so the way to do that is we can actually flip the direction of that position as long as we flip the sign of the position. Okay, and so that's going to become 920.0 meters to the west plus 1,360 meters to the west. Okay, and so the idea is whenever we want to flip the direction of a vector, we can do that as long as we flip the sign of its magnitude. Okay, and so then we can add these two together. Now we're adding instead of subtracting. Okay, but we're adding them together because they have the same direction now. And so that's going to give us a total of 2280.0 meters to the west. Okay, so in trip number 2, we were displaced 2,280 meters, only we're displaced to the west. Okay. All right, now we're going to do trip number 3, and then we're going to do all 3 trips together. So we'll do the displacement now for trip 3. And so same thing, we're using our final position minus our initial position. For trip number 3, let's just go back to our diagram for a second. For trip number 3, our initial position is going to be that 920 meters to the west, and our final position is going to be that 340 meters to the east. So final position is 340 meters to the east. Our initial position was at 920 meters to the west. Okay, and so again, we have the wrong directions here, and so we're going to flip this second one so that it's going to also be to the east. So it'll be 340 meters to the east plus our 920 meters now to the east since we flipped its direction. So that's giving us a total of 1,260 meters to the east for our displacement for trip number 3. Okay, now if we want to do the displacement for overall, we're just going to do the displacement from each. So trip 1 plus the displacement from trip 2 plus the displacement from trip 3. Okay, so our displacement from trip number 1 was 1,360 meters to the east. So we've got 1,360 meters east. Our displacement for trip number 2 was 2,280 meters to the west. Oh, it was 2280.0. 80.0 meters to the west. And then our displacement for trip number 3 was 1,260.0 meters, also to the east. Doesn't want to draw east today, apparently. All right, so we can't just go ahead and add those together because they're not all in the same direction. Okay, and since we have 2 that are going in the direction to the east and only 1 that's going west, I would suggest we flip our west vector so that it's to the east. So now it's going to be 1,360 to the east minus 2,280 to the east plus our 1,260 to the east. And so now we can actually add those together, and we're ending up with 340 meters to the east when we add those together. And so the trick with this displacement is that we want to use that formula, okay? And you want to pay very close attention to our position directions, because when we are trying to add or subtract vectors, we want to make sure that they are from the same direction, okay? All right. Now with displacement, okay, we don't actually care about intermediate steps. So if we go back to our picture here, okay, we know that we took trip number 1 and then trip number 2 and then trip number 3, and we ended up with an overall displacement just 340 meters to the east, which we could actually tell from the picture. Okay, and the reason for that is because displacement will not care about intermediate steps. Displacement is all about where you ended and where you began. Okay, and it is the difference between where you ended and where you began, and that's it. It doesn't matter how many routes you took to get there. It doesn't matter how many intermediate steps there were to getting there. Displacement only is concerned with final position minus initial position. Okay, it only cares where you start and where you end, and that's it. All right, so we are going to do some multiple displacements, only now we're going to look at some displacements that are perpendicular to each other. So we're going to look a little bit more into two-dimensional, rather than just traveling east or west, traveling on the same one dimension. We're going to look at some two-dimensional displacements. All right, so for this one, we're just gonna write this practice problem. Okay, so we have a car. Maybe if we can get it written down. So a car I'm writing too fast for the iPad. Okay, so a car moves. We're going to go 4 kilometers west, then 7 kilometers south, then 6 kilometers west, and then 4 kilometers south. Okay. All right. So first thing I want to do is I want to actually draw this on a grid, like on a graph, because it's much easier to see if we have it on a graph. So I'm just going to add my graph picture here from my library. Okay. So I'm going to draw all that information onto my actual graph here. All right, so I'm going to pick a point up near the top here that's going to be my starting point, because my car only moved to the west and south, and so I want to pick a starting point that's up near the top right. And I think what I'm going to do is use 2 boxes of my graph paper here for every kilometer. Okay, you don't have to draw it to scale, but I find that the first time we draw these, drawing it to scale is not a bad thing. And so for 2 boxes every kilometer, my car is moving first 4 kilometers to the west, so I'm going to have to go over 8 boxes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is my first movement. Okay, and so that was supposed to be my 4 kilometers. And so again, I'm just using 2 boxes in my graph here is equal to 1 kilometer. All right, so then we're going 7 kilometers to the south, so I want 14 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I'm going my 7 kilometers to the south. Okay, and then I'm going 6 kilometers to the west, so I want 12 boxes. 1, 2, 3, 4, 5. So that's my 6 kilometers. And then I'm going another 4 kilometers to the south. Okay, so 8 boxes. 1, 2, 3. So that's my 4 kilometers. Okay, and so then that's going to be my end point. Drawing lines where I don't want them. My iPad does not want to let me draw end. Okay. So there we go. Let's try this again. End, maybe? Let's try this one more time. Doesn't want to let me draw in my picture anymore. Just having some technical difficulties. Okay, so hopefully we got our picture drawn. What I wasn't able to put on my picture is that, let's try it one more time. There we go. Okay. Is that my displacement is actually from my start to my finish. So this is my displacement, which hopefully you drew in a better line than I did. It's very hard to draw in a straight line on an iPad. I can't use a ruler. All right, and so my displacement is actually forming this perfect right-angled triangle. Okay, and this right-angled triangle, the height of this triangle is 7 kilometers plus 4 kilometers, so it's 11 kilometers. And then the base of this triangle is going to be our 4 plus our 6 kilometers, so it's our 10 kilometers. Okay, and so then our displacement is from our start to our finish, and so it's just forming this nice right-angled triangle. Okay, so essentially what we're doing here is we've got this nice right-angled triangle. So we know there's a nice right angle here. The hypotenuse is our displacement. And we know that the height is 11 kilometers and the base is 10 kilometers. Okay, and so in order for us to find the displacement, we're going to use Pythagorean theorem. So our c squared is equal to our a squared plus our b squared. Okay, so c squared is going to equal our a squared. We'll use 11. I'm just getting all kinds of weird things on my iPad today. And our b squared is going to be our 10. And so then c is going to be the square root of our 11 squared plus 10 squared. And so we're going to end up with a c of 14.9. kilometers. Okay, now here's the problem. So that's the magnitude of our displacement. Okay, but we also need the direction. Now, up here at the top of our triangle, that was our start, and the bottom of our triangle here was our end. And so we actually want this angle right up here at the top, because our displacement goes from start to the end, and so it's pointed in that direction. Okay, and so we want to calculate that angle. So to calculate that angle, I would use tan. So tan of theta is going to be my opposite over adjacent. And so my opposite side is going to be the 10 kilometers. My adjacent side is the 11 kilometers. Let's try that again. So my tan theta is going to be 10 over 11. So then theta is going to be my tan inverse of my 10 divided by 11. And that angle is going to give me 42.3 degrees. Okay, so my overall displacement is going to be my 14.9 kilometers. And we're going to be south and then 42.3 degrees to the west. So we're going to be south, 42.3 degrees west. Okay. And the reason that I know that is because when we're looking at our triangle, that's the direction that we want to go in. First, we're going to the south, then we're going to the west. And so that's what we want in terms of our angle. Okay. Now, I want to give you another practice question that you can work on. And I'm going to give you, two practice questions to work on for displacement. that then we will take up later. Okay, and so the other thing that I want to talk about is distance. Okay, so displacement is the difference in position from start to finish. Distance is just is actually the traveled length. Okay, so if we were looking at this problem that we just did, okay, where we went 4 kilometers to the west and then 7 kilometers south and then 6 kilometers to the west and then 4 kilometers to the south, our displacement was only 14 or 14.9 kilometers, okay, but our distance traveled would have been 4 kilometers plus 7 kilometers plus 6 kilometers plus 4 kilometers. And so in that problem, we would have traveled 21 kilometers. And so that would have been our distance. And so distance is actually just delta D with no vector. Okay, it's just the sum of all positions moved. So in our previous problem, the distance would have been, so we'll just put our distance up here, would have been that 21.0 kilometers. Okay, distance is a scalar. It has no direction. Okay, and distance is the actual distance traveled. So whatever you actually do, whatever you walk or whatever the car drives, or that's distance. Okay, and then displacement is the difference between the start and the finish. Okay, distance is the actual path that we take. Okay, and one big thing is that distance, while distance and displacement could be equal to each other, distance is usually larger. Or equal to displacement. Okay, one big important thing though is that distance has no direction. Displacement does have direction. Okay, distance can be larger than displacement, or they could be equal. Displacement can never be larger than the distance traveled. Okay, so if they're equal, that's fine, or distance could be larger. Displacement can never be larger than the distance traveled. Okay, and so that's it for looking at the beginning of kinematics: position, displacement, and distance. And there's some practice problems to keep working on in terms of displacement. Okay, when we do displacement problems, we also usually are going to look at the distance, but distance usually just involves adding up the distances that were traveled. Okay, doesn't matter which direction you traveled those distances. Distance is just the sum of all the movements that you actually made. Okay, displacement is when we are looking at the difference between our final position and our initial position.